Here we are at the beginning of our Algebra 2 journey. We're going to wrap up our Algebra 1 knowledge, and to do so, we're going to quickly review through chapters 1, 2, and 3. So we're going to start out with chapter 1 review here. I'm going to basically go through the examples in the review section of the chapter, just going through and that way providing a little bit of extra explanation to these things, a little bit more context. Hopefully these things feel like review. If there are a couple new concepts, we're going to make sure we want to be solid on those before moving forward. The first thing we're going to start talking about are real numbers and number operators. So basically, these operations are going to be things like adding, subtracting, addition, subtraction, all that stuff that we've done before. And now we're just talking about where these things lie on a number line. So our negative numbers are going to be to the left. The more negative you are makes you a larger negative number, but it's still less. So I would rather owe somebody $5 than owe somebody $1,000. I would rather have $10 than I would rather have $2. So again, bigger positive means larger, and we're hopefully able to write these in increasing order. So we see here, -4 on the number line is to the left of -1. Although 4 is a larger number, it's negative, so it's to the left. So bigger negative over here. Here I have 0.3, that's just a decimal. So here we have 3/10 or 0.3, and that's going to be to the right of 0. Here now we're in the positive range. Here I have √7. So √7 is just some nasty number. We represent it with square root of 7 like this, and that's going to be greater than square root 3. So we know that the square root of 4 is 2, and the square root of 9 is 3. So when we think about what the square root of 7 is, it's somewhere between those two. And we don't need to know exactly what this number is, and this is actually an irrational number. So when we get down to talking about what whole numbers are, what integers are, and what rational numbers and irrational numbers are, the whole numbers are just those counting numbers we use that include 0. The natural numbers are just going to be the positive portion right here. So when we talk about natural numbers, it's just going to be the whole numbers nix out the 0. So I'll put a little natural numbers note here. So when we talk about these things, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And if we're doing whole numbers, then it's 0, 1, 2, 3, 4, 5, 6, blah, blah, blah. Integers, however, can be negative. So here's our counting numbers, but now we have negative as well. So -3, -2, -1, 0, 1, 2, 3, etc. This little triple dot here just says, okay, continue the list in either direction. Our rational numbers are just the numbers we can write as a fraction, and we can sometimes write these as decimals too. Now the decimal may not be terminating, so say for example we're looking at 3/4. 3/4 is a terminating decimal at 0.75. If I do 1/3 though, this is a decimal that does not terminate, so this is going to be repeated forever. So the term for this, sometimes you'll see people write 0.3 and they'll write the little line above it. That's a vinculum. So the vinculum basically just says, okay, this thing goes on forever, and that would look like, something 0.3, and they'll sometimes do a line over it. So that little vinculum is just denoting the same as this 0.333 and then ... But all of these are rational numbers. Basically, again, I can write it as a fraction, I can write it as a decimal if I want to. But now we started getting into this concept of, well, what if I couldn't, right? So there may be something that I can't write in a nice repeating pattern like this, or maybe it doesn't terminate. And that's where we get into this concept of, what if I take the root of that number, or what if I have a special value like pi? Okay, so pi is really cool. We have the geometric application for it as it relates our circumference to our radius in the circle, but we don't have an exact value for it. We just use pi as our little representation for what is approximately, 3.14. Is it exactly 3.14? No. And we can keep going to 3.1415926, blah, 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 but there's really no need to do that. We just use pi as an exact representation for that irrational number. Doesn't repeat, doesn't terminate. Cool. Just leave it as it is. It's messy. We're okay with that. We do the same for these roots. So when I don't have a root of a nice number, so say, for example, I was doing with square root of 100 is just 10. When I deal with the square root of 2, it does not have a nice answer for me. And so I just leave it as square root 2, and we would refer to it as an irrational number. When we're looking at properties for addition and multiplication here, we want to talk about what the different properties we have. So this is different if I were talking about subtraction and division. Okay, so just keep in mind that we're referring to addition and multiplication here. The first one we're going to look at is closure. Closure basically just means I can take two numbers, add them together, and I still get a real number. Now, we see this term real number, and we're not really sure what is not a real number. That's actually an imaginary number or a complex number, and we'll get to those later on. But for right now, we just need to know that if I hand you two numbers and you add them up, no matter what they are, it could be positive positive, positive negative, or negative negative, you're still going to end up with a real number. The same is true for multiplication. Again, it's a little bit boring if we multiply by 0, but it's still a real number. The next thing we're going to look here at is the commutative property. Commutative property, is basically just saying, hey, can I swap the order I do these things? So instead of doing 2 plus 3, could I do 3 plus 2? Yeah, absolutely, and we get the same answer. It's because this property holds true for addition. This does not hold true, for example, with subtraction. 3 minus 2 is not the same as 2 minus 3. So just keep that in mind. Works for addition, does not work for subtraction. We have the same in multiplication. 2 times 3 is the same as 3 times 2. Our associative property. So for our associative property, it's basically saying, can I do a couple of the things first, as we denote with parentheses, and then do the other thing? And that is going to be denoted by the parentheses as well. So for example here, if I had 1 plus 2 plus 3, could I add the 1 and 2 together first? Yeah, absolutely. And it's going to give me the same answer as if I did 1 plus 2 plus 3 and I added the 2 and the 3 together. Vice versa, if we want to change this thing around and start adding the 1 and the 3 together first, that would be okay as well. So associative just says, does it matter which one of these 3 things I end up doing first, or 2 things, or 5 things, how many additions, subtractions are separating them? And this is true for addition. It is also true for multiplication. So if I'm multiplying 2, 3, and 4, it's the same thing as if I multiplied 3, 4, and 2. My identity here is basically just saying this thing is itself if I do this thing to it. So if I add 0, I'm just my original number. So 10 plus 0, still just 10. If I wanted the same for multiplication, I'm just saying multiply by 1. Any number times 1 is just the original number. Inverse is an interesting concept. We kind of think about this as, how do I get back to where I started from? And so we'll sometimes talk about this as like, how do you neutralize something? So if I had 3, for example, how do I get back to 0, right? How do I get back to nothing? Well, if I had 3, I would add a negative 3. So I'd subtract 3, and that would bring me to 0. That's the inverse of 3, and that's an additive inverse. If I was doing multiplication, I would need to be doing some sort of division, or I can think about it as multiplying as 1 over the number. So if I had 5 times 1/5, for example, it's going to be the same thing as if I wrote 5 over 1 times 1 over 5. When I'm multiplying fractions, top multiplies with the top, bottom multiplies with the bottom. I get 5 over 5, which we simplify to 1. So here again is just bringing me back to where I starting at 1. So if I have a number times that number's reciprocal, so 7 times 1/7, for example, it's going to bring me back to 1. The only exception here is we cannot have a value of 0 because we can't divide by 0. Last one here is our distributive property. So distributive property is going to be taking a value that is outside a set of parentheses and multiplying to all of the things within the set of parentheses. So this A is going to go to the B, and the A is going to go to the C. I'm going to write out one more slightly more complex version of this, which is if I had A, let's do B, let's do C, D plus E. Okay, so this A is going to go to each one of these 3 terms. And I'm looking at this and saying, okay, well, A times B is AB. A times CD is going to be ACD. And then I've got my plus AE at the end. So again, just distributing to each of these terms. What's separating these terms is either an addition or subtraction sign. So CD, for example, is just one term. These two multiply together, but the B and the E are separated by these addition signs in between. Next, we're going to look at algebraic expressions and models. So basically, when we're looking at these, we're just starting to introduce this concept of maybe we have some variables. When we look at numerical expressions, we have different ways of representing them. So I may not refer to myself as being 10 plus 6 years old. I would just say I am 16 years old. But the actual math behind it is true and the same. So when we talk about numerical expressions, we just want to know, especially of our order of operations, which is the thing that I'm going to do first. So let's scroll down a little bit just to get some PEMDAS action going on here. So when I write out PEMDAS, I'll typically write it out once like this, but then I am going to change the way that I write it to represent more what it is that I'm doing. So I'm going to write this out again, and now I'm going to write it P, then I'm going to put EM on the same level, I'm going to put DA on the same level, and I'll have my S at the end. When I am looking at this, oops, that's not how I would do it. I would do it more like P and then E, MD, AS. That's better. Cool. So when I'm looking at this, I'm doing my parentheses first. So the first thing I do is my parentheses. And so when I'm looking at a problem, I'm seeing something like this, I do whatever is inside of those parentheses before I do anything else. Now when I'm looking at doing the stuff inside here, maybe I have exponents. Well, that's great because exponents are the next thing I'm going to be looking at. So I want to make sure I'm evaluating my exponents before moving on to M and D, which is multiplication and division. So here we have our multiplication, oops, M-U-L-T, kind of sneaking in there, that's bad handwriting. We can do better than that. M-U-L-T, multiplication, and D-I-V, division. Now these things happen with the same priority, and so the way that we organize this is we go from left to right. It's that simple. So when we are at this step of doing multiplication and division, we just read it just like we read a book from left to right. We do the same thing with our last step here with addition and subtraction. So sometimes you'll see little things online that'll be throwing people into a tizzy about, well, how do you evaluate this little formula or something like that. It'll just be some numerical expression and people will be arguing how you do PEMDAS and all that. You can always win the argument just by knowing how it actually works, which is that it goes from left to right. People will screw this up all the time. It's a little bit tricky, but this is the actual order of operations, how we follow it. So looking at this numerical expression, for example, to start us out, we see 3 plus 4 squared, and that's inside parentheses. I've got an 8 on the outside. That's going to be multiplication. So I'm going to highlight this as a thing on the outside. And then I've got this stuff going on the outside as well. So I'm trying to just represent the fact that this is orange and this is red. So I'm going to do this orange stuff first. Well, the thing that I do inside of the orange now is going to follow the same. I could have additional sets of parentheses. That's totally fine. Maybe a little bit messy. So typically what we'll do is we'll break it up into brackets. So sometimes you'll see something like this, where we've got stuff on the inside of a parenthesis and maybe plus and then some other stuff like this, and then we'll have it inside of another bracket. So this is, again, just nested parentheses, just written in a different way. So now jumping back into this problem here, I want to do this thing inside first. Well, here I've got a 3 plus 4 squared. I'm going to be doing my exponent. So this 4 squared is 16. So that turns into the 16 here. And now from here, I'm just going to say, okay, well, again, I'm still evaluating this set of parentheses. So my next step here is going to have me evaluate for this. So this is 3 plus 16 is 19. So I'm going to rewrite this as 8. I have 19. Now here on the outside, I'm going to leave it as my subtract 12 over 2. Although if you wanted to simplify it as our minus 6, you can. I'm just trying to keep this one step at a time for us here. So now looking here, I'm looking at multiplication on the left, and I'm looking at division on the right, and they're being separated by a subtraction. So here I want to actually do the multiplication division as I see it, left to right. Well, 8 times 19 is going to give me 152. So here I got 152, and then here I have minus, and this is 12 divided by 2. 12 divided by 2 is 6. Minus 6, and now as my last step I do my subtraction. 152 minus 6 gives me my 146. Looking at an algebraic expression where we have variables, if I wanted to evaluate with a specific variable, I may get something like this, where I say when x equals negative 5. So what we need to be able to do here is plug it into wherever we see x's. Now the reason I've circled this first part is the second part is just a constant, it's just -1. So there's no x that I'm plugging in here, but there definitely is an x that I'm plugging in right here. So looking at this one here, I'm saying, okay, well 3 times, and I'm doing this thing squared. So I'm going to write it out as -5, which is my x value that I want, squared. Keep in mind that whenever I have a negative times a negative, it becomes a positive. So here now, this is where I get my positive 25. I'm leaving the -1 on the outside, and I'm leaving the 3 on the outside as well. So here's my 3 from before, here's my subtract 1 from before. 3 times my 25 will give me 75 here, my -1 along for the ride here, and now as my last step I do the subtraction. 75 minus 1 is 74. Good to go. Sometimes we'll use our distributive property here. So when we're looking at this, I think most people would think of this as combining like terms and they wouldn't really use the distributive property, but I'll explain kind of what the text is doing here. The text is saying, hey, you have -4x's here and 10x's here. What we're actually doing here is we're factoring out an x. So we're factoring out an x and leaving whatever's left on the inside to do whatever it's going to do. So here we have -4 plus 10. Well, -4 plus 10 is 6. So that's how -4x plus 10x turns into 6x. So just keep in mind that whenever I have an x raised to a power versus just an x that I see or a constant, we're not going to be able to combine those things together. So if I had x squared plus x plus 1, there's nothing I can do with this. This is fully simplified, good to go. I love that answer. If I had x squared plus 3x plus 2x plus 1, I would not say this is fully completed yet. We want to simplify by combining our like terms here. So this would simplify to be x squared plus 5x plus 1. When we are looking to solve our linear equations, we basically want to get all of our variables to one side. The first step that I'm going to do is make sure all the variables are on one side. It really doesn't matter whether it's the left or the right. Maybe if you're left-handed you think differently. I'm right-handed, so typically I'll want the left side of the equation to have the x and the constant to be on the right. I have no idea if anyone is different in their brain preference. I'm guessing there's a million different ways you can do it in terms of your thought process, but typically we'll throw the variable on the left, constant on the right. As you do these, the first step is we want to do whatever the problem has set out for us. So here we have a distributive process here. We have a -2 on the outside being multiplied by this x minus 4. Keep in mind that it doesn't just go to the x, it's got to go to both terms. When I have a negative times a positive, it's going to turn it into a negative. So that's why I have -2x here, and I have a negative times a negative, which gives me a positive 8. So now I'm looking at -2x plus 8. I've done all of my distributive stuff. I don't see any sort of exponents or anything else like that that I have to do anything with. So now I'm looking at, okay, well, how do I get this x thing by itself? I have two options. One is I can subtract this 8 over and then divide. I would say that's what I would do. But you can also add 2x to both sides. So in terms of what we have available to us here, I'll try and sneak it all into one screen at once, but I'll probably zip back up in a second here, is we have our addition property, subtraction property, multiplication property, and division property. And all each of these is saying is that you can add the same number to both sides if you want to. You can subtract the same number to both sides if you want to. You can multiply the same number to both sides if you want to, so long as it's not 0. Can't multiply 0 to both sides because that basically just nukes the whole problem. And we can't divide by 0 as well. So when we're looking at this, if we want to multiply or divide to both sides, that's fine. Just don't do it with 0. So jumping back up here in our example, I'm going to say we want to subtract off 8 from both sides. So I'll take a little 8 off here, take a little 8 off there. So here I am going to be left with -2x is equal to, and now I have 12 minus 8 will give me 4. So now to get the x by itself, I'm going to need to divide by -2. So I'm going to divide by -2, and I'm going to divide by -2 over here as well. Keep in mind that if you have some number of x's, the only way to get the x by itself is to multiply or divide. If I had 1/2 x, I would have multiplied by 2. just as an example. So here I'm going to divide by negative 2, divide by negative 2. I get my final answer here of x equals negative 2. We always want to take our answers and plug them back in to check our work. Let's just say, for example, we wrote down a messy number here. It didn't look like an 8, it looked like a 9 at the time. So we did all of our work, we got an answer. When we get that answer, we want to check to make sure that it is valid. So we take it and plug it in. So I go back to my original equation here, and instead of writing it with the x, I'm just going to say, okay, well, I know my x value, or I think I know my x value is negative 2. That is the negative 2 that we're plugging in right here. So now I have negative 2 minus 4, which is negative 6. Now I have negative 2 times negative 6, which is 12. Does 12 equal 12? Yep, last time I checked it did, so we're good to go. When we're rewriting equations and formulas, we just want to keep in mind that we may not be solving for an actual answer here. So if I have 2 or more variables in one equation, I'm not going to get some sort of nice answer. It's always just going to be this variable equals these other variables. So when I'm looking at problems like this, I really just want to solve for whatever I'm asked to solve for. Here I just want y. And so when I'm looking at a problem like this, the first thing I'll write out is y equals junk. I don't know what the junk is, but I'm going to figure it out right now. So this is what I want my thing to look like, my final answer. To get the y by itself, what am I going to do? I'm going to get rid of everything that's not y, and I'm going to get all of the y's on the same side. So here I just have one y. My life is pretty easy. I'm going to subtract 2x from both sides. Now the reason I'm subtracting 2x is I want the y by itself. So that's now going to leave me with negative 3y equals negative 2x plus 6. My next step is to get the y by itself, so I'm going to divide by negative 3. Keep in mind that when I divide by negative 3 here, I'm dividing by negative 3 to both terms. So if you want to write it out as 2 separate divided by 3's, you can, totally up to you. My final answer here, I would say would be acceptable to leave like this, but if you wanted to split it out, let's split it out. So the first thing that splits out is I would have negative 2x over negative 3. The negatives are going to cancel off, so here's where we get our 2/3 x, and I got my minus 2 on the outside because I have my 6 divided by negative 3 gives me a negative 2. So my final answer could also look like 2x over 3 minus 2. Now if you write your answer like 2x in the numerator and then 3 in the denominator versus 2/3 times x and the x is kind of off to the side, that's totally acceptable. Both of these mean the exact same thing. So when we're looking at it like this, it's really like saying x over 1. So when we're writing this out, 2x over 3 means the exact same thing as 2/3 x. I typically will opt for this version, and the reason is that if this x is in the denominator, these are actually different things. So if I had 2x over 3, that is different, does not equal 2 over 3x. So just keep in mind that when we're doing this, if this is written in an ambiguous way, which this tends to be a smidge more ambiguous depending on the handwriting, it's just safer to throw it right in the numerator there. We can do the same thing in any sort of formula. So here we have area formula for a trapezoid. Again, not something you really need to know from geometry. It would be really nice if we remembered these things. They are kind of useful, especially when we're looking at trying to maybe do like some sort of construction project or something like that. But for this section and for our intents and purposes for this class, these formulas will be provided to you. I'm not looking for people to remember these things. So the thing that I want here is I want to solve for h. So in every step, I want to keep in mind that I want h by itself, and I'm going to do that in a couple different ways. So one way is that I could distribute this 1/2, distribute the h, and then I could go through and divide everything back out, but that doesn't do me any good. So the first thing I want to note is that as I look at this, I kind of want to look at this as blocks. I look at this 1/2 as a block. I look at b1 plus b2 as a second block, and I look at h as a third block. So really I've got 3 terms that are being multiplied. If I want to get this h by itself, I would divide off these other 2 things. So again, just because these are being added inside the parentheses doesn't make it any different. It's still just multiplication here. So as I look at this, how do I get rid of 1/2? Well, there's two ways to think about it. One is you can divide by 1/2, or two is you can multiply by 2. Either way, it's doing the exact same thing, so however you choose to think about it, totally fine. I'm also going to divide off this b1 plus b2 thing, and if you want to do it as 2 separate steps, that's totally fine. So just for instructional purposes here, let's do it as 2 separate steps. So instead of thinking about it as divide by 1/2, you could think about it as multiply by 2. So I'll just hit the whole thing with a 2. Sometimes you'll see the work shown out like this, where you wrap the entire thing both sides in a set of parentheses, and then do a 2 on the outside to distribute to both sides, and that will bring us to this next line here. My last step, again, is just to get the h by itself. To do so, I'm going to want to divide by my b1 plus b2. And you can keep that wrapped in parentheses, or you can kind of leave it just sitting by itself, b1, let's see, plus b2. And now we get our final answer here, which is the h is equal to our 2a, all divided by b1 plus b2. You don't need to wrap this denominator in parentheses. If you want to, that's totally fine. So here is where algebra becomes really useful, is trying to determine different problem-solving strategies. So here where we're looking at problem-solving using algebraic models, we're basically saying, okay, I'm going to give you some information. I need you to figure out something, right? So in the vaguest terms, that's what we're doing with these things. We know that distance equals rate times time. So this is the sort of starting point we have here. Now there's a lot of different applications for things, whether you're looking at distance, rate, and time, or whether you're looking at maybe like a degree. So say we're doing some chemistry project, we're trying to raise the temperature of a certain thing and observe some sort of chemical reaction. So maybe we're looking at like Fahrenheit to Celsius conversion. Like there's a lot of different applications, but we're just going to start out looking at this one. These are things that will be provided to you, right? And I can make up all sorts of silly ones as well, but really it's just that we're following some formula, and there's going to be a couple inputs to determine our output. So in this example, we're seeing how far can we drive at 55 miles per hour for 4 hours. Well, I'm told the rate is how fast I'm going. So my rate is 55 miles per hour. I know how long I'm doing that for. That's my time. So my time here is for 4 hours. So when I'm looking at my equation, I know this piece right here is time, this piece right here is rate, and I'm trying to solve for the distance. So if I were to do this in colors, just to keep it super simple, the red dot is equal to the orange dot times the green dot. Now I have values that I'm going to fill in for this. I'm going to use a variable d to represent distance, and that's going to equal, and here I'm going to have my 55 miles per hour times my 4 hours. So this is going to give me a total of 220. I could change things around as well and say, okay, you traveled 110 miles. So again, this is just a new problem, another example of the application here. If you traveled 110 miles, and you were going 55 miles per hour, how long did you travel for? So here now we don't know the t. So again, in this problem we have 3 variables. We're told 2, and we find the last one. Now I can only find the number of variables as the number of equations I'm given, and that's assuming they don't coincide, like I give you the same equation twice. So when I'm looking at distance, rate, and time, if you tell me 2 of them, I'll always be able to solve for the third. So here I've given us distance and rate, but we don't know time. So this would look like 110 equals 55t, and then I would divide by 55 to solve to get t by itself, and I get my t value equals 2, and we're good to go. So again, just showing you that we can take any one of these things, punch it out, give the problem to somebody else, and they should be able to solve for it. Solving linear inequalities is very, very similar to solving linear equalities. It's just that we have a range of values. So if I said, okay, I'm 5'11", is there somebody taller than me? Sure, There's somebody who's 6 foot, 6'1", 6'2". So the answer to this thing is just taller than Mr. G. Well, taller than Mr. G is a whole range of values. It's actually an infinite number of values that are taller than me, although, some of them are less realistic than others. So when we look at this, we really want to try and get the variable by itself, and we want to say, okay, well, what does that mean for us? Is it a strictly less than, or is it less than or equal to? And we'll talk about what that means in a second. So let's just start out with this inequality, which is 4x plus 1 is less than 7x minus 5. Now, the only time that we change this sign is if we multiply or divide by a negative number. If we do that, we must remember to flip the sign. That's the biggest thing people forget to do here. So the first part of the problem is going to be the same. I want to get everything together on the same side. Let's say we subtract 1 from both sides, and let's say we also subtract 7x. So I'm subtracting 1, I'm also subtracting 7x. You can do this in 2 steps, or you can do it in 1 step. Now, 4x minus 7x is going to give me negative 3x, and here I have negative 5 minus 1 gives me negative 6. So now we're looking at, let's do it in another color here. So now we're looking at negative 3x equals negative 6. Well, what do I do with that? I want to get the x by itself, so I'm going to divide by negative 3. I'm going to divide by negative 3. Keep in mind, this is the thing that we do, which is that we flip the sign when we multiply or divide by a negative number. So we flip the sign when we multiply or divide by a negative number. So looking at this, it used to be negative 3x is less than negative 6, but now I'm going to change that. So now I'm going to say this thing on the left, negative 3 divided by negative 3 just gives me 1. So 1x, x, is greater than, flip the sign, 2. This is now my final answer. When I want to represent this thing graphically, I'm going to use an open circle at 2, and I'm going to open to the right. So x is greater than 2. I'm going to rewrite this thing, 2 less than x. These two are exactly the same. There's no difference between these two things I have circled in green here. The only thing different is the order which I've written it. But again, the sign is flipped here. They mean exactly the same. So when we're doing these, please, please, please don't let this be you. Don't make this mistake. It does not orient with the direction of the symbol, okay? So whether this thing is pointing to the left or pointing to the right, it's still just going to be whatever the actual numerical representation is. So here we have x greater than 2. What is greater than 2? Greater than means everything to the right of 2. And why is this just greater than? So is 2 greater than 2? It's not. It's equal to. So that's where we get this open circle from. We use an open circle when it's strictly less than or greater than. So this should look like an open circle with everything to the right filled in. We may have a range of values here. So here I have 0 less than or equal to 6 minus 2n less than or equal to 10. When we're given a problem like this, we still follow the same steps. Just keep in mind that you're doing it to each of the 3 areas. So each inequality is going to hold, and then if it changes, it changes, right? If we flip it or whatever like that. So the first thing I would say we do is subtract 6. We want to get the the negative 2n by itself. So subtract 6 from everywhere, subtract 6 from everywhere. So now I get negative 6 less than or equal to negative 2n less than or equal to 4. My next move here is going to be just divide by negative 2. Keep in mind that only when we multiply or divide by a negative number, we flip the signs. This is getting flipped, and this is getting flipped. Negative 6 divided by negative 2 gives me 3. 4 divided by negative 2 gives me negative 2. Negative 2n divided by negative 2 is just n. So now here's where we get our final answer. Now keep in mind, I'm going to rewrite this one more time. Say negative 2 less than or equal to n less than or equal to 3. These two things circled in purple here are exactly the same. There's no difference between them other than the order which we've written it. So when we look at something like this less than or equal to means I have a filled in circle. So I have a filled in circle at 2, it should be -2, and a filled in circle at 3. Now again, my n values are greater than -2, so I'm going to go to the right, and my n values are less than or equal to this 3. So basically what that means is they're going to meet up in the middle. I'm going to shade everything in between them. So I should have 2 closed circles versus the open circle we had over here, and I'm going to shade in between them. Let's say, for example, I had something that looked like this. -5 is less than, oops, let's do this. I don't want to do -5 because then I'm going to be off this little scale here. I want to try and represent it. So let's say -1 is greater than x, and we have x is greater than 2. Do it like this. In this scenario, we would have an OR junction between these two things. So it'll often say this or this, and a lot of times you'll see a comma separating them. So here I'm saying my x value is less than -1. So open circle here, shade to the left, or I can have x is greater than 2. Open circle here, shade to the right. So in red is just how I would represent graphically this answer here. Still a totally acceptable answer. A lot of times this will be talking about tolerances outside of a given range. So say for example, we're looking at I don't know, the height for a ride. So we're saying that some ride was perfectly designed to be ridden by a person who's exactly 5 feet tall, and the ride only allows for those who are within that sort of tolerance. If you're going to be within a certain range, then you're going to be looking at this purple example here where I cannot be too tall and I cannot be too short. So that would be something where we would be within the two inequalities, versus something like the red example we have here would be outside, would be something that like breaks a tolerance. So say for example I was making Cheerios, right? This is the size of Cheerio that I want. This little green Cheerio is too small. Anything smaller than that is too small. Anything bigger than this is too big. So when I'm looking at, okay, well, what is outside of this range? We'd say Cheerios past that get rejected, and Cheerios within that get rejected. So again, just another way of using tolerances. And you can also flip it and say, okay, well, the range inside there is what is acceptable. So you kind of take the flip on that and talk about it in terms of excess or in terms of constraints. That is it for our Chapter 1 review. This is just a summary of everything that goes through the sort of process for solving these things. Add same to both sides, subtract same to both sides, multiply or divide is fine. It's just that when we get to multiply or divide by a negative, we got to reverse the inequality. So flip the sign there. And the last section in Chapter 1 is solving absolute value equations and inequalities. So when we're looking to solve an absolute value, we want to keep in mind what an absolute value actually does. So if I look at the absolute value of 5, for example, I use these little vertical bars to represent an absolute value. The absolute value of 5 is 5. The absolute value of -5 is also 5. So whatever is inside here, whether it's positive or negative, the absolute value of that value is going to be positive. So when I look at solving a problem like this, I'm basically solving for these two different scenarios, one in which the inside is actually positive and one in which the inside is actually negative. So looking at this first example here, let's take a peek at x plus 3. And actually I'm going to use a different color because I like to use red and green here for positive and negative. So let's do an orange. We'll say x plus 3 is equal to, we'll change it up a little bit, we'll make it 7. So if I said x plus 3, the absolute value of x plus 3 equals 7, I want to solve this thing. I'm going to solve by branching off. I set one branch to be my negative branch, and I set one branch to be my positive branch. So the reason I'm doing this again is because I can have a positive and a negative inside of my absolute value that will still spit out the same answer. Still going to give me 7. So looking at the negative version of this, I'm going to throw a -1 on the outside, so it just looks like a negative sign. And then on the inside here is going to be my x plus 3, and I'm going to say equals 7. I'm going to do the same thing, except for I'm going to throw a +1 on the outside here, so it doesn't look like anything. and I say x plus 3 equals 7. Now I'm going to solve for these two individually. So again, I should be getting two solutions here. There are some scenarios where you'll just get one answer because you're looking at the vertex, but most cases we'll have two solutions here. So looking at the first one here, I can either distribute my negative sign or I can divide by -1. I'm going to divide by -1, or you can multiply by -1. It's the same thing. So now I get x plus 3 equal to -7. I'm going to subtract off my 3, and I get an x answer here of -10. If I take -10 and plug it in here, I would say -10 plus 3 is -7. The absolute value of -7 is 7. Check. Works out. The next one here, I'm just going to subtract my 3, and now I get x equals 4. Good to go here as well. Looking at this answer, if I plugged it back in, 4 plus 3 is 7. The absolute value of 7 is 7. Check. We have our two answers, x equals -10 and x equals 4 here. Now the thing that would change about an inequality is that when we multiply or divide by a negative value, we have to flip our sign. So this is the biggest thing that people forget to do, is they forget to flip the sign. So let's take a peek at an inequality here. So let's make up an example. Let's call it x plus 1, and we're going to say that is greater than or equal to 3. So looking at this greater than or equal to, I'm going to do the same setup where I branch off to the left for my negative version and the right for my positive version. In my negative version, I'm going to throw my little negative sign on the outside of whatever's in my absolute value. So here is x plus 1, and I'm still going to leave the sign the same as greater than or equal to 3. I'm going to do the same for the green here. It's a positive 1 on the outside, so it should just look like x plus 1 greater than or equal to 3. Now looking at this one on the left, I want to multiply or divide by -1, or if I wanted to, I could distribute this as well and then do my next step, which is going to be multiply or divide by -1. Doesn't matter which way you think about it. I did the division right off before, so here we'll do our distribution. So let's distribute. So now it becomes -x minus 1 greater than or equal to 3. I want to get this x by itself, so I'm going to add 1 to both sides. And now I'm going to divide by -1. Keep in mind that when I do any division or multiplication with an inequality, I have got to flip the sign. So now it's going to be x is less than or equal to -4. There's one of my answers. If I plug in -4, it will work out exactly. -4 plus 1 gives me -3. The absolute value of -3 is 3. 3 is greater than or equal to 3, so that works. If it was strictly greater than, then it would not work. So let's pick a value less than -4, say -5. -5 plus 1 gives me -4. The absolute value of -4 is 4. 4 is greater than or equal to 3. So we see this checks out. Good there. Let's do the simple version here. We're going to subtract 1 from both sides. Here I'm going to say x is greater than or equal to 2. And I am good to go. Here, if we were to graph this thing, we would be looking at a graph that looks like a filled in circle at -4, a filled in circle here at 2 because it's greater than or equal to, and less than or equal to. And I'm looking at where I would shade. So my x is less than or equal to -4, so I would shade to the left over here. And then I would shade to the right over here. X is greater than or equal to 2. One thing we want to note is that if I swapped the position of this thing and wrote it as 2 less than or equal to x, and if I swapped the position of this thing and said -4 greater than or equal to x, it doesn't change the meaning at all. These two are still totally the same, and these two are still totally the same. There's no difference depending on how we write it. The actual inequality remains consistent. So when we're solving these things, we're going to just remember that one rule where if we multiply or divide, we have to flip our sign. So for inequalities, we got to remember to flip the sign there. So when we're solving these things, we're going to follow these steps. It's going to have one positive, one negative version. And when we're looking at transformations of absolute inequality, this is basically what we're talking about when we talk about doing, okay, well, what if I wanted to say, I'm within a certain range, I'm going to have my absolute value is less than a value. Or if I want to say I'm outside of a certain range, I'm going to say greater than a certain value. So if we jump back to looking at this problem right here, we said that x plus 1 was greater than or equal to 3. So here again, when we're looking at a greater than instance here, instead of greater than or equal to, we're outside beyond that range. So we're basically going to get one answer heading in one direction, the other heading in the opposite. If we did an example like this, we would have the two close in on each other. It's only ever one or the other. So I'm either going to be between these two values or outside of the two values. It's always going to be that way. If we have them both pointing in the same direction, we want to make sure we go back and check our work.